Okay, greetings everyone. This is a tutorial video on how to find area or approximate area bounded by a curve. So we have a problem here, and we're going to do this in using the four different ways we do this. And so we're always bounding the area bounded by a curve and the x-axis in some way. And in this example here, the curve on this interval from 2 to 5 is entirely above the x-axis. It could be that the curve does dip below on the interval that we're doing the approximation, but that's not here for this video. We're going to use just three either rectangles or trapezoids, three left-hand endpoint rectangles, right-hand endpoint rectangles, midpoint rectangles, or trapezoids. All of these problems start in the exact same way. We're just finding the area of some shape. And so once we know how to find the area of the shape, we just got to find those values and then do the calculations. And so for rectangles, it's the base times the height. And for those, we've got to, start by finding out how wide each rectangle is going to be. So we're doing this from the interval from 2 to 5, as it says right here. So x equals 2 to x equals 5. If you feel like going, marking up the screen or your graph or whatever when you're sketching this, you can. So it's all of this area under here that we're trying to approximate. But again, we're not finding it exactly, so I'm going to get rid of this. We're going to be using some rectangles. So I got to find out how wide the rectangles are. This is a fairly easy example, but the more complicated examples work the same way. We're gonna name our width of our rectangle delta x, and we always calculate delta x the same way. It's going to be b minus a divided by n, where the a and the b are the endpoints of the intervals. A is our left endpoint, b is our right endpoint, and n is the number of rectangles or trapezoids that we're using. So in this example, n is always going to be 3. B is 5 and a is 2. And I made it fairly, like I said, an easy example for the calculations here, because I want you to understand the process more than I want you to be bogged down by the complicated numbers that might come up. So numbers for some of this are going to be fairly easy to generate. So B is 5, it's the right-hand endpoint. A is 2, it's the left-hand endpoint. And N is 3, it's the number of rectangles or trapezoids that we're going to be using. And since 5 minus 2 is 3 divided by 3, the width of our rectangles is 1, which is going to make the calculations nice and easy in part of this process. So if my width of my rectangle is 1 and I'm starting at 2, that means I'm going to move over 1 unit to get the next end of my rectangle. So my next end of my rectangle is going to be at 3, and then my next end of my rectangle after that's going to be at 4, and then my next one is going to be at 5. What we typically do for that, you'll see me write this down all the time, is we label these things with as x values with subscripts. X sub 0 or x naught, N-A-U-G-H-T, x naught, is always your left-hand endpoint. So this starts off to be 2. And then we're going to keep adding delta x to the 2 to get the new endpoint, just like I did over here in the picture. So x sub 1 is going to be 2 plus 1 or 3. X sub 2 is going to be 3, the previous one, plus that delta x, which is going to be 4. And x sub 3 is going to be 4 plus 1, which is equal to 5. Notice that x sub 3 being 5 is our right-hand endpoint. That should always happen. If we calculate our delta x correctly, we start in the right spot, and we keep moving accordingly by adding that delta x each time, we should end up at B. And if we don't end up at B, then we have a calculation error, and we need to go find that error before we continue on. So these are our endpoints. We always start at x sub 0 at the left-hand endpoint. This is x sub n. Remember, n is 3 in this problem, and so my last endpoint, my right-hand endpoint, will be x sub n, in this case x sub 3, and that got us 5. Now to do the approximations using right endpoint rectangles or left endpoint rectangles or midpoint rectangles, it's only going to require us just to find the heights of the rectangles now, because we got the width, that's delta x. They're delta x units wide each, and so Now all I got to do is find out how tall they are, and once I know how tall they are, I'll be able to calculate the area of each rectangle, and then I'll add them up to get the approximation. And so if I'm using left-hand endpoint rectangles first, that means I'm going to go to my first subinterval. My first subinterval goes from 2 to 3, from x sub 0 to x sub 1. I'm going to go to the left-hand endpoint. I'm going to trace upwards until I hit the curve, which is right here, and then I'm going to draw a horizontal line from left to right. That's going to give me the top of the rectangle. I'm going to continue that process. I'm going to go from over the next subinterval from 3 to 4, go to the left-hand endpoint, go trace up the curve until you hit trace up until you hit the curve. Now you can see I didn't draw the vertical line very well. It should be on this line right here. And then I'm going to draw from left to right all the way to the next endpoint. Now notice that this line didn't go up high enough, but that's okay. I can just extend that a little bit like this. And then I go to the last subinterval from 4 to 5. I go to the left endpoint 4, trace up until I hit the curve, and draw a horizontal line from left to right to the other endpoint, and just complete the rectangle. So for my left-hand endpoint rectangles, those are the 3 rectangles that I'm going to find the area of and add together to get my approximation. Now, how do we get those heights? Well, remember, the heights are just found by I didn't say this, so I'm going to say remember. You should be remembering from pre-cal, but I haven't said it yet in this video. Remember, I traced up though up the value 2 until I hit the curve right here, and this length is the height of the rectangle. Well, this length is just the y coordinate of the function. In other words, all I have to do is plug 2 into the function f, and then whatever output I get, that value is going to be the height of the rectangle. The width of the rectangle, or the base, is just 1. That's our delta x. And so if I take 1 and multiply it by f of 2, I'm going to get the area of this rectangle. For the next rectangle here, again, I'm using left-hand endpoints. That means I'm going to plug on this interval from 3 to 4, I'm going to plug the left-hand endpoint into the function f, and that's going to give me the height of that rectangle. And then I'm going to multiply that by the width 1, and that'll give me that area. And then for the third rectangle, I'm going to do the same thing. I'm going to plug in the left endpoint, which on the last subinterval is 4. I'm going to plug that into the function f, take that y coordinate that comes out, the output of f of 4, multiply it by 1, and then I'm going to add those 3 values together, and I'll get the area using left-hand endpoints. So let's just write that down. So I'm going to put just a little a sub L over here. So the area using left-hand endpoints. Now remember, the actual area is something different. So the actual area, if I just call that A, is approximated by the left-hand endpoint rectangles. And so I'm going to write this down. It's going to be f of 2, which is the height of the first rectangle, times 1. Now, I know times 1 doesn't do anything, but I'm going to write it down anyways, just so you can see the process, because the width of the rectangle is very rarely going to be 1, but because it is, it's easy to calculate in this example. I still want you to see it there for now, so when it's not 1, you know what to do. So I'm just taking the heights that I talked about over there a moment ago, and I'm just multiplying by the base, 1, and then, like I said, we got to add those areas together. Now, to get the value f of 2, again, all we have to do is plug the number 2 into the function f. So if I go up to my function f, I'm going to plug 2 in up here. 2 minus 4 is negative 2. Negative 2 to the third power is going to be negative 8. I'm going to write this down so I don't forget it. Then I'm going to multiply 2 times negative 2, and I get minus 4. And then plus 15. That's all f of 2, which looks like 3 times 1. That's going to be 3. Then I'm going to plug 3 in up there. 3 minus 4 is negative 1. Negative 1 cubed is still negative 1. And then 3 times 2 is 6, so minus 6, plus 15. Then I'm going to multiply by 1. That looks like 8. Put a plus sign in here, and then plug in 4. 4 minus 4 is 0, so that's nice. I don't have to cube. 0 cubed is still 0, so minus 8. That's from the 4 times 2, so you get a negative 8 right there because we're subtracting, and then plus 15. So that looks like 7. And so it looks like our area is about 18 using left-hand endpoints. That's our approximation. Now later on in this class, we'll figure out how to find this value exactly, so it's not an approximation, but that's just our approximation. Now, if I want to use right-hand endpoints, let's go down to the picture here. For right-hand endpoints, I still starting at 2 and going by 1 unit, so it's 2 and 3, 4, and 5. But on the first subinterval, I'm going to, instead of going to the left-hand endpoint 2 and then drawing a horizontal line from left to right, I'm going to go to the right-hand endpoint 3, and I'm going to go to where that value hits the curve, and I'm now going to draw a horizontal line right to left, and then complete the rectangle. And then I'm going to go in the next interval from 3 to 4 and go up to the curve, draw again right to left, and then from 4 to 5, I'm going to draw right to left as well. And these are the 3 rectangles that I'm going to find the area of and then add together to find the approximation. So this one here is f of 3. This one here is f of 4. Values already found. But now this one here is f of 5. And so my area in this example is approximated by the right-hand. These things are all called Riemann sums, by the way, and I'll tell you that name again later, named after a mathematician, George Frederick Bernard Riemann. But nonetheless, again, all these problems here start with the same thing. You find delta x, then you find the endpoints of your subintervals, and then you go through finding the area of the rectangles. So for the right-hand endpoint rectangles, remember it's now f of 3 is our first value times 1, plus f of 4 times 1, plus f of 5 times 1. We already know f of 3 is 8. We know f of 4 is 7 and times 1 because we did those up there. Now, I don't know f of 5 because I haven't worked it out yet, but if we go back up here and we plug in 5, 5 minus 4 is 1, 1 cubed, still 1, minus 10 is minus 2 times 5, and then plus that 15. So this is going to be 8 plus 7 plus, it looks like 6. Yeah, because 1 minus 10 is negative 9. Negative 9 and 15 is 6. So it looks like our area is approximately 21 using our right-hand endpoint approximations. Now, if we want midpoint approximations, what I'm going to be doing, instead of plugging in the left-hand endpoint into the function, I'm going to be plugging the midpoint into let me start that over. Instead of plugging the left-hand endpoint in, instead of plugging in the right-hand endpoint, I'm going to plug in the midpoint on each subinterval. So I'm going to start the same way. I still need delta x, and I'll calculate it as b minus a over n, which is 1 in this case. I'm still going to start a at 2, and then move over 1 unit to get x sub 1 to be 3, x sub 2 to be 4, and x sub 3 to be 5. All that's exactly the same. But the difference here is, and my rectangles are may look a little bit funny this time, but so be it. Some of these lines are going to be a little too tall, is what I mean by that. Now I need to go to the midpoint of this interval. The midpoint between 2 and 3 is 2.5, right? We all know that. So I'm going to look at 2.5, and I'm going to go straight up until 2.5 hits the curve right about here. And then I'm going to draw to the left and complete the rectangle, and then draw to the right and complete it if I have to. This is the rectangle that I'm going to need for a midpoint approximation on the first interval. Between 3 and 4, I'm going to go to the midpoint there. But I'm not going to draw a vertical line because I tend to get confused. So I'm just going to trace up without making the line, and then go to this point, go back to the left, go to the right. I don't like how that one came out. Let me do it again. And not much better. Complete the rectangle. And then between 4 and 5, go to the midpoint, go up here, hit the curve, go to the right, go to the left. Those are the 3 rectangles I'm going to use to approximate the area bounded by the curve here. What did I do to get the height of the first one? I went to the midpoint. The midpoint's 2.5. Now, just to make sure we can do this in other situations where it's a little bit more complicated, let's recall x sub 0 is 2 for this example, x sub 1 is 3, x sub 2 is 4, and x sub 3 is 5. So my first midpoint, m sub 1, I'll always do this. I will always take x sub 0 and x sub 1, and I'm going to add them together and divide by 2. I'm going to average them. Add them together and divide by 2. That's 5 halves, or 2.5. So that's how I'm always going to start finding my midpoints. Now, if my rectangles are nicely formed like this, all I have to do to find the next midpoint is keep adding delta x like we did earlier. So all I have to do is add 1 to 2.5 to get the next midpoint, and then add 1 again to get the next midpoint. I could, although I don't want to because I'm lazy, I could just do this averaging thing again on each subinterval. I could go to x sub 1 and x sub 2, add them together to get 7, and then divide by 2. 7 divided by 2 is 3.5. And then for the last one, I could add the 4 and the 5 and divide by 2, and I'll get 4.5. But in more, where the numbers look a little bit more complicated, it's easier and faster if I just take delta x, which was 1, and I just keep adding it to each new midpoint. That way, the calculations are more efficient. So you can get them either way, but more efficient, in my opinion, just to take the first midpoint that you found by averaging and then continue to add delta x. So our area now is approximated by the midpoints, which I'll call a sub n. And the first midpoint is going to be plugged into the function. You get 2.5, and then f of 2.5 times 1, and then f of 3.5 times 1, and then f of 4.5 times 1. And again, we're multiplying by 1 because that's how wide the rectangle is. So in a different problem, you're going to have a different width probably for the rectangle. So you don't want to multiply by 1 in those examples. You want to find out what delta x is and multiply it by delta x. And then you'll do this calculation. Again, you'll actually, your area is approximately whatever we get from that. I don't have that number in front of me, so let me go see if I can find it. So this will give you about 20.625, if I'm remembering it correctly from another screen. You should make sure that you can get that calculation yourself. And again, you're just going to plug those values, 2.5, 3.5, and 4.5, back into the original function up here. And that way, you can see it over here off to the left as well, I guess. And that way you can generate those values and then do the rest of the calculations yourself. Now, for trapezoids, we have to remember how we find the area of a trapezoid. So the area of a trapezoid is found by adding together the bases and then multiplying by the height and then dividing by 2. Or one way you can think about this is it's the average of the bases, base 1 plus base 2 divided by 2 times the height, or it's the sum of the bases times half the height. There's lots of ways of remembering this formula. When I teach it, when I taught geometry way back when, I try to give each interpretation for the students because some like different interpretations better. We start the same way. We're going to go to x sub 0, which is 2, and x sub 1, which is 3, x sub 2, which is 4, and x sub 3, which is 5. We're going to draw in those endpoints. We still find delta x, b minus a over n. We still find the endpoints of our subintervals. Now, this time, though, to find draw in the trapezoids, what we're going to do is we're going to draw in a secant line, which means we're just going to connect the outputs at the two endpoints of the subinterval with a straight line. Pretend that's a straight line. Maybe I could do a better job if I try it one more time. Nope, that didn't work. What I'm going to do, again, is try to connect those two with a straight line. If you have a ruler and you're doing this on your page, it would be better. And then one over here. Again, not very well, but those are your trapezoids. Most of you remember trapezoids from your earlier class. Maybe it looks something like this. And your bases were these two parallel sides here, and your height was the distance between them. Well, in this picture here, our bases are the vertical sides that go like this. These are the bases. These are the parallel sides. This is base 1 and base 2 of the first trapezoid. And the height is how far apart they are. That's our delta x. That's our h in that picture. H in this picture here is our delta x. And so we're just going to repeat that, 3 times and then get a value, and then we'll have our approximation. So A is approximately, I'll call this A sub t. So the first base, well, I need this length right here. We've already calculated that before. That's just what I get by plugging 2 into the function. So that's f of 2. But I'm going to put this, as f of 2. And then the next one, I just got to plug in 3. That's f of 3. And then I got to multiply by delta x, which is 1. And then because the formula has a divided by 2 in it, or a 1/2, that's what we're going to get. That's the first trapezoid area. The next trapezoid has a base that's f of 3 on this side and f of 4 on this side. So we're going to get f of 3 as base 1, f of 4 as base 2. We still have the height of 1, so that's multiplied there, divided by 2. The last trapezoid, f of 4, is the base 1, f of 5 is base 2, so f of 4 plus f of 5 times the height divided by 2. And I don't remember that calculation. I'm going to go look at another screen. Well, that one you should get 19.5. That's how you do it. I'm going to stop this video here, and I'll do another example with the number, with the values being slightly more complicated. But it's the same process, ladies and gentlemen. You did it in pre-cal. You got to do it again here. It's not that challenging. You just got to practice and make sure you can do it consistently and accurately when asked. Go